So, good afternoon, everyone. My name is Ron, and it's an honor to present our undergraduate research in this year's conference. Under the distinguished guidance of Dr. Joseph Ortenera and Dr. Raymond Tan, we dive into the world of energy storage technologies. So we all know the importance of renewable energy in the world today. It is the blood of our society, powering our cities, cars, and innovations. As such, one of the most prominent sections is points of interest is towards energy storage systems, or more specifically, energy storage technologies, which is and while there are many different ways to transfer technology, we've mainly focused on those for electrical applications, or as we define it, technology that harness electrical energy provided by various sources of energy, converted to a form that is suitable for storage. There are many different types and classifications of ESTs, all based on the nature of how they transfer and store energy. So, for example, chemical energy storage, they work on the principle of bond dissociation and the formation of reversible chemical reactions, such as with that in a hydrogen fuel cell. They store energy through generated hydrogen bonds. And others follow the same principle, such as with electrochemical ESTs, which uses redox reactions, such as with batteries, lithium-ion, nickel-cadmium, lead acid. And then electrical ESTs, they use electrical energy, such as capacitors and supercapacitors. And for thermal ESTs, they use the thermal energy generated through chemical reactions to store energy, such as that with sensible heat and latent heat technology. And on the opposite side, we have mechanical ESTs that use a physical medium that collects kinetic and potential energy. Physical mediums such as fast-flowing air for compressed air, running water for pumped hydro, and rotating wheel or flywheel. So this leads us to the purpose of our study. Which EST is the best, or more specifically, which EST is the most capable? Because unfortunately, not all ESTs store and transfer energy equally. And the definition of the best EST can change greatly depending on the application. And as such, that's where the problem lies. How do we evaluate something like an EST with many complex variables? So let's take a look of our evaluation criteria, which we divided into two categories. The technical criteria, consisting of power capacity. Power capacity is the maximum amount of energy that technology can store. Power and energy density is the amount of energy that can be stored per unit volume. And cycle efficiency and storage lifetime, which measures the longevity of the technology. With cycle efficiency, it's how much energy is retained per each charging and discharging cycle, while for storage lifetimes, it's how many cycles before the technology starts to degrade. And of course, we have to consider the economical aspects, such as the power and energy capital costs, which measure how much, how expensive the cost of storing energy. And as such, we cannot use traditional single attribute decision-making methods, because it's not about which EST has the lowest cost and which one can store the most energy. There are many complex variables, like what we talked about earlier. For example, maybe power density is more important than cycle efficiency. So how do we do that? And the answer is we developed a MADM methodology, or multi-attribute decision-making, which is based on a limited number of alternatives that are subjected to multiple attributes that are considered complex and conflicting, which fits our data quite well. And more specifically, we wanted to use the MADM methods of AHP and Viker. So for our methodology, the two parts are done with the first half being AHP, followed by Viker. AHP, we determine our evaluation criteria, whilst Viker, we use it to evaluate and rank the EST alternatives. And for EHP, the principle of it is to determine the relative importance of each of the attribute in the form of criteria weights by creating a pairwise comparison matrix, where each attribute is compared to each other and a relative value of importance is assigned to each comparison. However, we aren't qualified enough to answer the questions of the comparisons, because how would I know if the power capacity and the power density is much better? So that's why we reached to experts who are much more knowledgeable on ESTs to fill up the comparison matrix. And we sent them this form, and in the end we got the opinions of 9 experts to do it. So after that, we did our aggregation of all the experts' opinions, and then we did the AHP method, and we got our criteria weights. And from their response, we are looking for a consistent opinion on the relative importance of each attribute, which leads us to the second part of our methodology, which is checking the consistency of the result. And the general rule of thumb is that the consistency ratio must be less than 0.1. And this is also integrated into the AHP process itself. So once we check it, we see that our opinion, the opinion of the experts, is consistent. So it passes that check. That's with our criteria weights determined. We move into the third part, which is the evaluation via Viker. However, we have to get the data first, which is the specifications of each EST, which we gathered from a review done by Kui, Fei, and Rosen in 2020, which you can see in this table. Afterwards, we use the EST data table as input to the Viker, and our previously calculated AHP criteria weights as our evaluation parameter, which leads us to the final ranking. So as we can see, capacitors is the best EST, followed by pumped hydro, flywheel, then pumped hydro, then lithium ion, and the worst ESTs is sensible heat and hydrogen. And another important aspect to consider in the Viker method is what's called the Viker index parameter, because in the Viker process, it ranks each alternative by calculating the maximum utility, which is a measure of an alternative strengths, and its individual regret, which is a measure of an alternative's weakness. So the V value, as we call it, determines how much weight the maximum utility will have in the ranking. Thus, a V value of 0, then the individual regret will be prioritized, which means an alternative with the lowest R value will be the best alternative, which is the one with the lowest weakness, while a V value of 1.0 is where the alternative with the highest S value will be prioritized, and V equals 0.5 is when they're both equal. So we perform sensitivity analysis by changing the V value and seeing how it affects the ranking. And as you can see, the top 3 is solidified. There. So the top 3 is solidified despite that, which means that they have very consistent strengths and weaknesses, as well as the bottom 2. And then we also perform sensitivity analysis by changing the criteria values of the 2 least important attributes for EST, which is power capacity and power density. Since during stationary power applications, power capacity and power density is not really that important, since they measure the amount of energy released in bursts. So a much more better attribute is energy density, because it measures the amount of energy for a long period of time. So we wanted to see what it is, how it affects it. And as you can see, as power capacity goes up, it becomes more and more important, that top 4 becomes lesser and lesser in ranking. And what does it tell us? It tells us that power capacity is a weakness. It's a great weakness for capacitors in the top 4. But since power capacity is not that important, that's how they got their high ranking. And the same can be said with power density. So in the end, what's the point of these graphs? What do they tell us? They tell us that while, yes, lower ranking ESTs such as hydrogen fuses and capacitors are banned for long-term electrical applications, that doesn't mean that they're all the while useless. Because for power applications, that's just like in a short term of time, they are more better for that application. So, can I have one more minute? Okay. So in conclusion, what can we say about this? So basically, we find out that cycle efficiency and storage lifetime are the two most important attributes for a good EST, and that supercapacitors is the best overall EST because it exhibits the two most important attributes. But that doesn't mean that supercapacitors is the best for everything, since supercapacitors is a relatively young storage technology, so it's still developing, and it's not really recommended for large-scale applications. And we also found out that AHP Vicar is an effective tool in making complex decisions like this. So yeah, that's all. Thank you.
So now, question and answer portion. Okay. So anybody who would like to ask questions?
Sure. Hello. Sir, I have two questions. First, being not so knowledgeable on your topic. So, I don't think I got what is AHP or NVCOR are. So, can you elaborate on those further? And I just say my second question.
Okay.
So can you go to the slide where you show the parameters or criteria that you have considered? Yeah, the technical and economic criteria. So while you consulted experts on the ranking of this criteria, so have you also consulted to them if these criteria are really the only criteria that needs to be considered when evaluating the best EST? Because, for example, I'm thinking about like safety and other criteria. So have you considered asking them those?
So to answer your first question, AHP and Vicar is a MADAM method, which is a way of ranking, and basically it's a decision-making process. And for AHP, it's about the AHP is determining the criteria, and Vicar is actually using that criteria from AHP to rank those alternatives. And
sorry, does it mean something like AHP?
yeah, AHP is analytical hierarchy process, and Vicar it's too long, honestly. So I abbreviated it. So, but usually when in the statistics area, when you talk about AHP and Vicar, it's already, that's the more known name. And to answer your question on the technical criteria, to answer yes, there are many different criteria. That's why supercapacitors, some of the biggest cons of supercapacitors are not considered. This is like just our scope and limitation in a way. There are other different ways, but we wanted to limit our scope because just like what I talked about, MADAM works best when the scope is small, and that's what we did here. Like for example, for supercapacitors, they have a low cycle duration and a high self-discharge rate. And as you can see, we did not consider that there. So if we did, then maybe the ranking of a supercapacitor might go down a little bit.
So any more questions?
My question is, I'm just curious because the first two, I'm just gonna focus on the first two, the top two. You mentioned that supercapacitors or flywheel are the highest ranking. So in the Philippine setting, because we already have battery energy storage systems already installed in the grid. So is this somewhat, does this particular ranking somewhat illustrated in the Philippine setting? Because flywheel is not yet parang hindi siya popular dito sa Philippines. So what does this tell about the research results?
That's a good question. And like I mentioned before, supercapacitors, it's a relatively young technology. So while it has so much promise, while yes, technically it's the best for most electrical applications, it's still lacking in application sense, so it's all in numbers. But when actually there's no large-scale operation using supercapacitors in that way, so to answer that, in Philippines, you're right. It's mostly lithium ion and pumped hydro, but we're in here. This is more of a general world sense because we based our data on a general review back in 2020, and what I mentioned was that if supercapacitors since it's not really good for large scale large scale applications, then this ranking shows up alternatives like flywheel, pumped hydro, and lithium ion for that, and I guess that's what it is in the Philippines.
I'm just curious because you mentioned about technical ranking. How does it compare, with regard to economics?
Okay, so we didn't really discuss that, but if we look at the data, we mainly focused in this presentation on the supercapacitor since it has the highest storage lifetime and cycle efficiency. So from the ranking, we can assume that flywheel and pumped hydro and lithium ion, they're like, even though they're not as comparable, they still have a high cycle efficiency and storage lifetime because those are the two most important technical attributes for ESTs.
Yeah, but if you want to build some big plant, you have to take a look also with its financial viability, like the IRR, the return on investment, interest rate, the
Yeah.
payout period.
Yeah,
etc.
the only things that we considered for economic is the capital cost. So that's one of our limitations of our research, which it's ranked as the energy capital cost is like the third most important.
Any question or? Any? Well, I only have one question. Where did you get the data? I mean, the data was taken from what's the name? From the other first movie. Is that the only source of your data? And would that be suffice to give you a good conclusion?
We took this data because it's the only comprehensive review of ESTs, of all ESTs that we have. So we thought it is actually a good baseline for what ESTs is, like a good representation of what it is right now. So of course, some of the data, they're not the most recent, but it's a good representation of how ESTs are. So that's why we used only one source and we didn't want to jumble up. We wanted to point the source to one area.
Any more questions? So if there is no more question, then we will proceed. Thank you very much for your question. So that's